Okay, so when we last left off, we were discussing reactions of thiols and sulfides. So in this case, we previously discussed that thiols can be oxidized to yield disulfides or oxidized to yield sulfoxides and sulfones. So in this case, we're dealing with and we're continuing the problems that we were working through last class session. And now we're looking at an example of product prediction. So in this case, we're asked to predict the products for the following reaction. So in this case, we have a free thiol and we're treating it with chlorine. So let's take a few minutes and consider these reaction conditions, and then let's try to comment in the chat or verbally, or you can even draw a structure of the product on the class whiteboard. What are these conditions going to accomplish? So if we treat a thiol with a halogen, what are we going to form? What are we going to make? So let's take about 1 to 2 minutes to think about these reaction conditions, and then I'd like to see some proposed responses shared in the chat or verbally. And if anyone's feeling particularly ambitious, you can try and share the mechanism for this reaction. So if we treat a free thiol with chlorine, bromine, or iodine, what product will we observe? Would anyone like to share their perspective in the chat or verbally? So we know that thiols are generally quite liable to oxidation. So we're not using a hard oxidizing agent like hydrogen peroxide or dichromate. Instead, we're dealing with a relatively electrophilic or soft oxidizing agent in the form of chlorine. So what happens when we expose a thiol to a relatively mild oxidizing agent? What really important functional group would we generate in this process? So to give everyone a hint, I'm going to draw one of the first steps in this mechanism just to help us start our thought process. Yeah, the lone pair on sulfur will attack the electrophilic chlorine. Yep. We've now activated our sulfur atom as an electrophile. And now from there, now that we have this activated sulfur-centered electrophile, our solvent can go in and pull off this proton since it's quite an acidic species. Okay, we now have this very electrophilic sulfur atom. And now that we have a second equivalent of thiol floating around, what is going to happen? And to give you a hint, just to give you a hint for this, you only need roughly half an equivalent of halogen to get this reaction to go to completion. Would anyone like to comment on that? So what's going to happen next? We have this electrophilic sulfur atom. We have a nucleophilic thiol floating around. So what would happen next? So we have an electrophilic sulfur atom. We have a nucleophilic thiol. So just like any displacement reaction, our nucleophile can attack our electrophilic sulfur atom. And what functional group are we making? What structural motif have we made? What do we call this functional group or structural motif with a sulfur-sulfur bond? What do we call this functionality? Right here. We talked about it last class session, and this is also covered in the reading. What do we call this functionality? A disulfide, exactly right. So treatment of a thiol with a halogen such as chlorine, bromine, or iodine generates a disulfide. These are quite useful conditions, and as we talked about last class session, disulfides appear abundantly in biological systems as part of protein structure. Okay, does this example make sense to everyone? So we talked last class session about oxidation reactions of thiols and sulfides, and one common way that thiols can be oxidized is via treatment with a halogen to make a disulfide. Does this example make sense to everyone? Any questions? Yes, please go ahead.
So whenever we treat it with the halogen, it's going to make two of that product, but one with the halogen and one with the hydrogen.
Yes. So the one with the hydrogen, this is just our starting material. So this is just our reactant.
Okay.
And part of the reason why you often use half an equivalent of halogen is because you only need half of your reactant molecules to be chlorinated. The other half you'd want retained as the non-chlorinated species, so it can attack as a nucleophile and form your disulfide bond. Does that make sense?
Kind of.
So essentially, the reason why you only need half an equivalent of chlorine is because you only really want half of your reactants to be chlorinated.
Oh, okay. I see
Yeah.
what you mean by the half of the equivalent. Okay, got it.
Mm-hmm. Perfect.
Okay.
Any other questions on this example? Okay, let's look at another product prediction example. This time we're treating a sulfide, not a thiol, but a sulfide with hydrogen peroxide and an excess of hydrogen peroxide. We don't have to draw a mechanism for this reaction, but what I would like us to consider is we're going to make an intermediate, and let's just make sure we're explicit on what does this intermediate look like and what is its oxidation state. Okay, and one way I like to remember this in terms of product prediction is I have two lone pairs to work with, and I'm treating it with two equivalents of oxidizing agent. So what product am I going to get out of this reaction if I treat a sulfide with two equivalents of oxidizing agent? So let's take about 2 to 3 minutes, and don't be shy to review the earlier pages of our note set that we discussed last lecture. And I'd like us to try to draw the intermediate structure and the final product structure for this reaction. So after one equivalent of hydrogen peroxide, you get an intermediate. The second equivalent gives us our final product. So what product do we get if we treat a sulfide with an excess of oxidizing agent?
Would we get a intermediate of methylphenyl sulfoxide?
Yep, exactly right. So after treatment with our first equivalent of oxidizing agent, we get a sulfoxide, similar to dimethyl sulfoxide. In terms of your name for this compound, it would be methyl cyclohexyl. The phenyl would look something like this.
Oh, that's right. Thank you.
Oh, but your proposed name was good. It was noting and attempting to name this compound following the IUPAC methodology for sulfides. So it was good. It was good. So we have our intermediate sulfoxide. And what happens after our second equivalent of hydrogen peroxide? what product would we get after the second equivalent?
Methyl cyclohexylphone.
Yeah, it's a substituted sulfone. Yeah. We haven't, and we won't cover the naming conventions for sulfoxides and sulfones. But do note that if you treat this sulfide, in this case, methyl cyclohexyl sulfide, with excess of hydrogen peroxide, you get the sulfoxide and then the sulfone. And sulfones can be quite useful. They're found as common motifs in certain high boiling polar solvents. And depending on the exact polarity and overall electronegativity you want for this sulfur containing functional group, it may be beneficial or needed to oxidize this sulfide to the sulfoxide or the sulfone. Does this example make sense to everyone? It's important to always just be familiar with how different reaction conditions modify our parent structure. Any questions on this example?
Does that say one equivalent?
Yes. So if you only used one equivalent of oxidizing agent, you'd get primarily the sulfoxide. If you use two equivalents, you get the sulfone. So you can get chemoselectivity via the equivalence of oxidizing agent. Did that answer your question?
Yep.
Perfect, perfect. So let's look at another example. So we've finished our problem-solving examples for chapter 18. So what we're going to do is I'm going to split this recording up